In this lecture, we take a look at energy for an object that is undergoing a rotation and a translation. The object is rotating about its center of mass, and this is all with respect to an inertial reference frame. The object can be rolling without slipping, or it could be undergoing a rotation and a translation such as this, for example. What we want to come up with is a description of the total amount of kinetic energy associated with those two types of motion. I'm going to first give you a detailed derivation that can be applied for any situation. And then secondly, I'll show you a nice short derivation for specifically the object involving a situation where it is rolling without slipping. Okay, but first of all, in general. Okay, kinetic energy for an object that is translating and rotating. Okay, once again, the rotation is about the center of mass. Okay, we're going to set up a Galilean relativity situation, actually. So first of all, we have an inertial reference frame O. We consider this to be at rest. Okay, and then here's a ball or something like that, like so. Right here is the center of mass, which coincides with the axis. We're also going to say that that is the origin of the moving reference frame O prime. So let's go ahead and draw in a second reference frame like so. This is the moving reference frame O prime. Okay, and then we're going to take a look at a small amount of mass that makes up this object. So for example, right here is a little m sub I. And then let's go ahead and describe some position vectors here for m sub I with respect to the two different reference frames. So we first of all have right here a position vector with respect to O. This is r sub I. Okay, right here is a position vector with respect to O prime. That's with respect to the center of mass. This is r sub I prime. And then we also have right here a third position vector. This is the position of the center of mass relative to the origin of the stationary reference frame O. So this right here is RCM. Okay, and then just doing a little bit of vector addition here, notice that RCM plus r sub I prime is equal to r sub I. So let's go ahead and write it like this. Like so. Okay, this right here is just the position transform from Galilean relativity. Okay, let's go ahead and take a derivative with respect to time to get the velocity transform. So if we differentiate this position vector here, we get a velocity vector like so. V sub I is the velocity of this point here with respect to the stationary reference frame. Okay, this then equals V sub I prime. That's the velocity of this point right here with respect to the moving reference frame, with respect to the center of mass. Differentiate this with respect to time and you get a VCM like so. That's the velocity of the center of mass relative to the origin, relative to the stationary reference frame O. Okay, now let's just write the total kinetic energy of this system as we sum over the I particles. So the total kinetic energy K is going to equal the sum of the kinetic energy of the ith particle. So what I'm going to do is just write a 1/2 mv squared. When I do, however, I'm going to be writing the V with respect to O, the stationary reference frame. So then therefore, the kinetic energy K is equal to the following sum of 1/2 m sub I v sub I squared, like so. Once again, this is just total kinetic energy. What I want to come up with, however, is a description of the total kinetic energy in terms of the translation and the rotation. So what I'm going to do is replace the v sub I here with this quantity right here, and I'm going to multiply it by itself. So I'm going to go ahead and write a dot product. I'm going to write it like this. Okay, I'm going to write the 1/2 out in front, by the way. Sum m sub I, and then v sub I squared. So this multiplied by itself. Like so. Okay, and then let's just go ahead and FOIL all of this out and then see what we end up with when we do. Okay, I'm going to have to switch to the lower board to do so. Okay, so kinetic energy K equals now 1/2, and we'll go ahead and write each term as we go. So 1/2 times sum over the I particles of m sub I, and now we have our first term. V sub I prime multiplied by itself. So v sub I prime squared, plus then 1/2 sum m sub I, like so. And then I'm going to have a v sub I prime dot VCM, but I've got two of them. So 2 times this, like so. Okay, and then I've got the final term, this times this. Like so. Okay, and now we've got to interpret what we have. Specifically, let's take a look at this term right here. I'm going to rewrite this term slightly. I'm going to write it like this. Let me do it down here, like so. So what I'm going to do is I am going to take the VCM and I'm going to bring the 2 and bring all of that out in front. So the 2 will cancel with this 2 right here, and then I'm going to have VCM dot sum m sub I v sub I prime, like so. So once again, this quantity right here is the same thing as this, just with a couple of terms rearranged. Now here's why I did that. Let's specifically take a look at this right here. This right here is a momentum expression. It's the momentum of the center of mass with respect to the center of mass. That's 0 by definition, and the reason for that is because the center of mass is the origin of the O prime reference frame. Here's another way in which you can think of this, however. This quantity right here is the derivative of this. It's the derivative of this expression. Like so. Notice that this expression here is the numerator of the center of mass equation, but it's specifically describing the position of the center of mass with respect to the primed reference frame. That's 0 by definition because the center of mass is at the origin of the primed reference frame. That's how it's set up, of course, on the diagram on the top board. So ultimately, that then means that this quantity here is equal to 0. Okay, this right here is the position of the center of mass with respect to the center of mass. So this middle term then therefore just drops out completely for that reason, like so. Okay, so now let me erase some stuff here and then let's clean up what we've got. All right, so let's get rid of all of this stuff. Okay, and now we've got kinetic energy K. Okay, we've got this term right here, V sub I prime squared. Let's now write the V sub I prime here, which is describing the speed of M sub I with respect to the center of mass. Let's write that as an R omega. Like so, where all of the particles that make up the object have the same angular speed with respect to the center of mass, because it's a rigid object. For example, as this ball rolls across the desk, or if it rotates and translates like doing something like that, okay? Okay, now let's go ahead and write this expression here. Notice in this expression that this right here is just the total mass of the object, the total mass of the ball, for example. Like so, which is just the translational kinetic energy of the object. Okay, now getting back to this term right here. Notice that this right here is a rotational inertia. It's specifically the rotational inertia of the ball as it rotates about an axis passing through the center of mass. So this right here is an ICM. And then therefore, you just end up with this. Clean this up a little bit. Like so. So the total kinetic energy of the system is nothing more than the two types of kinetic energy added together, the translational kinetic energy and the rotational kinetic energy. Once again, this expression here applies to any situation involving an object that's rotating and translating. So it can be rolling without slipping. It could also be doing something like this, like so. However, specifically for the case of the object rolling without slipping, deriving this expression here is actually only one step. Okay, let's go ahead and rederive this expression here, specifically for the situation involving an object rolling without slipping. Okay, so let's erase all of this. Okay, so now specifically, for the case of an object rolling without slipping. Okay, so here's a horizontal surface, here's my ball, like so. Here's the center of mass, which is moving in this direction like so, where VCM, and the object is rolling like this. Okay, we're just going to write this as a rotational kinetic energy, but specifically about this point. Remember, this point right here is sometimes thought of as the instantaneous axis of rotation, specifically earlier when I was talking about the kinematics of an object that was rolling without slipping. So this right here can now be thought of as the instantaneous axis, like so, and then therefore I'm going to write a rotational kinetic energy about that point, instantaneous axis of rotation. Okay, so then therefore the kinetic energy K is just going to be a 1/2 I omega squared, like so. Okay, now what is the I? The I is the rotational inertia of this object about this point. So think of it as my lower arm, for example, as my lower arm rotates around that point, like so. Okay, the omega is the angular speed, for example, say, of all points within this rigid object as we rotate around the instantaneous axis of rotation, like so. However, I'm going to take two terms there and replace them with the following. First of all, I'm going to replace the rotational inertia I with parallel axis theorem. What I'm going to do is move the axis of rotation from this point here to the center of mass. So recall parallel axis theorem. I equals ICM plus mh squared, where h is the distance from the old axis to the new axis. In this case, that's just the radius of the ball. So then therefore, I is going to be ICM plus mr squared. Let's go ahead and plug that into here. Like so. Okay, let's go ahead and distribute. Like so. And we end up with this. Okay, here's just the rotational kinetic energy that I had earlier. And then what is this? Well, recall from the kinematics of a rolling object that VCM is equal to R omega, where the omega we originally thought of as an omega about the instantaneous axis of rotation, but recall from the kinematics of a rolling object, that's the same as the omega as we rotate around the center of mass. So this right here is a V squared, but it's specifically VCM squared. So then therefore, we just end up with this. Like so. Same as before in the more general case when I did all the Galilean relativity and so on and so forth, but deriving this expression here for a rolling object is just literally one step. It's basically just parallel axis theorem, okay? All right, let's just go ahead and do a simple example involving an object rolling downhill. We did a problem like this dynamically a couple of lectures ago, but now in this case, we'll take a look at it in the context of conservation of energy. Okay, let me do some erasing here. Okay, so copy the problem down as I read it to you. An object rolls without slipping down a 30-degree incline through a height of 1 meter. Okay, the object was initially at rest. Use conservation of energy to find the speed at the bottom of the incline for the following. Part A, the object is a hoop. Part B, the object is a sphere. Okay, so we've seen this problem dynamically, of course, but now here it is in the context of conservation of energy. So here's our angle theta. Okay, what we're going to do is take a ball or hoop or whatever it is, and we're going to start it here at rest. We know it is equal to 0. Here's the center of mass. Okay, it rolls downhill. Here's the center of mass. The center of mass has a VCM at this moment, and that's what we're asked to find. And then the object undergoes a height change. Unless it says otherwise in the problem, assume that the height change is nothing more than the height change of the center of mass. So then therefore, if the height change in this problem is 1 meter, it's a 1 meter difference from here to here in terms of the height. So that's from this point here to this point here. That height change is given to us as 1 meter. In some examples, they may ask you to do a little bit more detailed analysis involving the dimensions of the hoop or the ball or whatever it is in order to get the height change. But if it doesn't say so explicitly, just assume that the height change that's given is just in terms of the center of mass. Okay, now there is friction in this problem. It's static friction, not kinetic friction. And does static friction do any work? No, it does not. So then therefore, even though there is friction in this problem, it is a conservation of energy situation. We do not have the non-conservative force of kinetic friction present. So then therefore, basically what static friction does from an energy standpoint in this problem is that it transforms some of the gravitational potential energy that we end up with, not just into the translational kinetic energy here as we move downwards in some manner, but also, of course, rotational kinetic energy as well. So we have to take into account the two forms of kinetic energy as we now set up our conservation of energy expression. All right, so 0 equals delta K plus delta U. We just start filling in our terms. So first of all, final kinetic energy down here, that's the combination of two things. It's going to be a 1/2 ICM omega squared, that's the rotational, plus a 1/2 m VCM squared, like so. Okay, then minus 0 for the initial kinetic energy, the object starts at rest. And then we just have our usual change in potential energy, final minus initial, like so. Okay, and then what we're supposed to solve for is VCM. So in order to do that, we need to replace the omega with the following. Once again, this is from the kinematics of a rolling object. Omega is equal to VCM divided by R, divided by the radius of the hoop, or whatever it is. Okay, so let's go ahead and plug that in here. Like so. And I now get to this step here, and it's at this point that we now begin to apply the equation for the specific situations that we're asked to look at. Okay, so first of all, part A, what we're given is a hoop. So ICM is equal to MR squared for the hoop. So let's go ahead and plug that into our equation on the top board. So 0 equals 1/2 times ICM, like so. And then times VCM squared over R squared. Okay, and then plus 1/2 m VCM squared, and then minus MGH. And now we can get rid of all of the radii here of the hoop. The R squared cancels out like so. So I have a 1/2 mv squared plus another 1/2 mv squared here. So that's just a total of mv squared like so. And now let's go ahead and move the MGH to the other side. So mass cancels out, and then just take the square root of both sides. So VCM equals the square root of GH. Notice that this is less than the square root of 2GH for an object that is translating, and the reason for that is because, recall, some of the potential energy is transformed into the rotational kinetic energy of the object, not just the translational kinetic energy. Okay, so we have the square root of 9.8 times 1 here. Let's see what that is to get our number. All right, square root of 9.8 is 3.13. Like so. Okay, and then let's take a look at part B of the problem. I have to move my file. Okay, so in part B, we have a sphere. So then therefore we have to change the value of ICM. It's 2/5 MR squared. So let's go ahead and back up. Okay, so for part B, the sphere, ICM for the sphere is 2/5 MR squared, and now let's go back up to our expression and plug in. So 0 equals 1/2 times ICM times then VCM squared over R squared, and then here's the translational kinetic energy and the potential energy, like so. Let's go ahead and get rid of the R squared here like this. Let's get rid of these 2's here as well. Now let's go ahead and do the math. This right here is 1/5 mv squared plus 1/2 mv squared. The common denominator between the two is 1/10. So then therefore this is 2/10 plus 5/10, which is a total of 7/10. So 7/10 MVCM squared, like so, and now we just run through the remainder. So let's move the MGH to the other side. so. Go ahead and cross out the mass, and then move the 10/7 to the other side and take the square root. Like so. And then this value here is a little bit bigger than it was earlier for the hoop. Remember, I demonstrated that, by the way, in my problem involving this dynamically a couple of lectures ago. But this quantity right here is still less than the square root of 2gh for an object just undergoing a translation. All right, so let's just go ahead and finish here. The square root of 10/7, and then times 9.8 times 1. And this all ends up being about 3.74 meters per second, like so. Okay? All right, so that concludes our look here at rotational energy involving an object undergoing a translation and a rotation.